Good afternoon. Please join me in welcoming Bill Perez, who is the Senior Global Product Manager for Clickbond, to talk about the benefits of bonding. Bill?
Thank you, Vicki. Good afternoon, Orlando. All right. First, let me start off. I'd like to thank AIAA for the opportunity for us to present a topic that's on the innovative manufacturing process, which is bonding. I'd also like to reach out and thank our Clickbond team for helping to put together this presentation that we're going to be going through today. And lastly, I'd like to thank my beautiful wife for her love and support on this journey. So thank you guys all so much. Our hope is today that this presentation will enhance your curiosity, the curiosity about what might be, about bonding and the potential that it provides. Ultimately, we hope that this presentation may change your whole approach when it comes to bonding. A little about me, I'm Bill Perez, a mechanical engineer and a global senior product manager here at Clickbond. For the past 25 years, along with our Clickbond team, we've been working with engineering partners that have built some of the most advanced aerospace platforms on the planet. Those engineers have built those platforms with the possibility in the high demands of the platforms that they're designing. Today, let's embrace what's possible and lead into the benefits of bonding. So it was those engineers that were embracing high performance materials. It was those engineers that knew that high performance materials meant that they needed to pivot away from traditional manufacturing processes. They needed to find a better way to build these aerospace platforms. Now, the power of bonding unleashed every single one of the applications you see here today. As you see on the board, many of the applications are common. You might know them, you might even work on them, but know that every single one of them has embraced the power of bonding. Now, we're not going to go into detail on any of those individual platforms today, but know that it was a time for Clickbond, and I'd like to reflect back on the click that changed everything. So let me take you back about 40 years. A pilot, entrepreneur, physicist walks out to his airplane one day and he notices a drip that comes from the bottom portion of the wing. As he walks forward, he realizes that drip, it's not water, but it's fuel. Now, in the aircraft he's flying, the wings are actually the gas tank. So now how do you repair that? Well, traditional methods would say that you would drain the wing, you would evacuate the fumes, then you'd drill out the rivet, replace the rivet, and fill the wings back up. That's a high-level description of this repair process. But I can tell you that the repair process could take a week or even longer. Well, for this pilot, this entrepreneur, this physicist, waiting that long wasn't going to work. He needed to have a solution that was faster and more effective. He challenged and said, why not seek an opportunity to seal that leak permanently and not remove that rivet? Well, he was already an established design engineer, had a knowledge of adhesives, and even knew a specific adhesive that could cure in the presence of fuel. So using that intelligence, he was able to, he was able to design a component that could work to seal that leaky rivet. This entrepreneur was Charlie Hutter, and along with his wife, Collie, who was a savvy business entrepreneur herself, with the click of a fixture, Clickbond was born. Now, this solution launched a company and a repair solution that allowed a small aluminum foil patch to be attached to the surface using an innovative application fixture that clicked as the adhesive cured. You can see some of the sketches below here that were the original artwork of Charlie at the time. Now, this patch not only repaired Charlie's airplane, but it was used to preserve similar aircraft that had leaky wings. One of them you see here on the screen, which is the F-16. So the click patch was applied to the wings of the F-16 aircraft and helped preserve that platform. This innovative solution was adopted not only to repair this aircraft, but wings of similar structure, all through bonding. So let's fast forward to today. We were told that airplanes would never be glued together. Who would ever think that you could glue an airplane together? Yet here on the screen are platforms that are indeed glued together. Now, in our industry, we don't like the term glued, but for this conversation, let's just use it as a placeholder. Notice on the screen, one of the most advanced fighters in the world. This aircraft was indeed glued together. Due to the platform's requirements, the aircraft required click bond fasteners to help hold that airplane platform together. It was those engineers who were pioneering with purpose. I want to take just a second, let those words sink in. Pioneering with purpose. I think it's an important aspect in the industry that we all serve here, that it's those people who are pioneering with purpose that can lead the way. It was those engineers that designed that platform that needed this innovative manufacturing method to meet the demands that were required of that airframe. When they realized bonding was the best solution, they embraced it and pushed forward. The results, as you see, are proven. So I ask, how many here are pioneering with purpose? I can tell you at Clickbond, being that trusted advisor on bonded solutions, it's that concept of pioneering with purpose that allowed our engineering teams to work with each one of the platforms you see here, helping them be successful. So, as we are here to discuss the benefits of bonding, let's take a minute to provide a high-level, simplified explanation of what is adhesive bonding. Well, if I were to look up a definition, it might read something like this. Adhesive bonding is a chemical reaction where molecular chain is formed by sharing electrons between the adhesive and the substrates. It's also a mechanical connection between the adhesive and structures held together. Ultimately, adhesive bonding is not one aspect. It's not just chemical, it's not just physical, it's not just mechanical, but it's a collection of all of these forces that overlap and influence one another. The key forces we're going to talk about today are going to be the mechanical interlocking factor, the electrostatic adhesion, and diffusion. Let's take a deeper look at each one. So first we'll start with mechanical interlocking. After abrading or sanding the surface, it'll create nooks and crannies in that structure. The wet adhesive will have the ability to flow down into the structure, creating these anchor effects, locking it in place. For mechanical interlocking, it's as simple as that. Let's look at electrostatic forces. Electrostatic forces are considered to be the forces of positive and negative ions. So as the structure is abraded, it increases the number of electrons at the surface, so the negatively charged particles, and they attach and mate to the positively charged particles. This creates that electrostatic adhesion between the two forces. But something that's a little bit simpler and easier for some people to understand is the example off to the right, where rubbing the balloon creates that electrostatic force and that force of attraction. The next force we have is adhesion. This is that contact in bonding that few people think about, but we'll give you an example that'll kind of lay it out. On the left-hand side, you have a water droplet that's full and round, sitting on the top of the structure. At this point, there's very little adhesion. When I move to the far right, you'll see the water droplet has fully flattened, creating a larger surface connection to the structure. At that position, that's the highest adhesion. Now, both of these water droplets are a function of the surface energy of that system. But know that in the middle, the function of surface energy is being calculated by the attack angle of the water droplet to the structure. The higher the angle, the lower the energy. The lower the angle, the higher the energy. We'll come back to surface energy here in a minute, but know for now that that's that contact for adhesion. The last slide we have is going to be diffusion. So you can look here and see that I've got a electron microscope example of how adhesive could interlock if the structure were the fixative. In this example, the adhesive has the ability to diffuse into the fibers or into the areas of the structure, creating a mechanical interlock as well. But remember that it's not going to be one specific force that increases adhesion for adhesive bonding. It's going to be a collection of all of these forces. So we mentioned a little bit about surface energy, but let's expand a little. On the screen, I've got an example to explain how surface energy is developed and how surface energy is decreased. Starting on the left-hand side with what we would call a new abraded piece of structure, you'll notice that the functional groups have no oxides, so no OH groups. As time progresses and we move to the right, you'll see that the oxidative groups are being built on top of the structure. For a newly abraded piece of material, this is going to be the highest surface energy. This will be the example where the water droplet is flattest. As we move to the right, the water droplet would bead up and sit on top of the structure. So what's a functional example that we can use that dispels or simplifies what surface energy is? Well, let's think about a waxed car. If you wax the surface of a vehicle and you spray water on it, what happens? The water beads up. When the water's beading up, it's telling you that nothing really wants to stick to that surface. So that surface is very slippery. If you were to remove the wax, what would happen to the water droplets? They would flatten out and completely wet the surface. That goes back to our water droplet theory. For 30 years, we at Clickbond have been experienced in doing the surface preparation and bonding. And as trusted advisors, we worked with our partners to develop processes to help maximize their bonding strength. Understanding the materials, understanding the science, and working towards helping them build processes to increase surface energy to also increase adhesive strengths. It's our teams working with our partners that allow us to work with the three phases of the development of their platform. The design phase, the build phase, and the sustain phase. So, as we dive into the benefits of adhesive bonding, I want to zero in on the 8 specific benefits. Benefits that you can realize. I have all 8 listed here. We're going to take an opportunity, we're going to dive into each one. The first benefit is it improves your cycle time. How can bonding improve your cycle time? Well, it eliminates the need for specialized tooling. It eliminates the need for specialized training. The Clickbond process would allow anybody that were here to replicate the bonding process and achieve the same results. If you think about the time, the example on the board is if you used a riveted nut plate, the process to swage the rivets and complete the installation might take you 3 minutes. If you simply replaced it with a bonded version of that same application, you could install that nut plate in 45 seconds or less. Ideally, a multiplier of 4. The elimination of the mechanically fastened processes, such as swaging rivets, saves time even before the action is recorded. You can see here that in this example, time savings can lead to improved rates, helping you speed time to market. That's critical in our industry, is getting to market fast. Number 2 is reducing foreign object debris. In aerospace manufacturing, FOD can be the enemy. By eliminating the need for rivets, bolts, and washers, you can eliminate the opportunity where FOD may slow you down. Remember, should you drop a bolt or a rivet in the aerostructure, everything must stop until that bolt or rivet has been received and accounted for. Number 3, it reduces production costs. We've had partners that have done time studies showing installation of 1,000 nut plates. For 1,000 nut plates, it takes them 374 hours, where installing bonded versions only takes 70 hours. So after all the time was tallied up for all the work that was done, we were able to save them 225 total hours of production time, which is approximately $12,000 of production costs. Significant on airframes. We simplify the installation. The 3-step bonding process simplifies the maintenance, simplifies repairs and maintenance. There's a surface prep that's completed, application of adhesive, installation of the component. Now we move into number 5, which is a very important aspect and a key benefit for bonding. It prevents corrosion. What you see on the screen right now is a riveted nut plate, its bonded counterpart, and them side by side. They were both subjected to 30-day salt fog, but if you look at the riveted version, you can see corrosion at the base, as well as corrosion in the nut element. Look at its bonded counterpart, and corrosion is not mitigated in the bonding surface. The picture to the right is just to exemplify that these were not tested individually, that they were tested side by side. And in the picture to the right, you can see the yellow hue, the golden hue around the base, which is indicative of corrosion. So to prevent corrosion, bonding is the better solution. We talk about bonding as it reduces weight. Yes, bonding does reduce weight. However, let's pause here for just a second and let's clarify that although bonding does decrease weight, there's a function that people don't think about. In this example, I've got 762 nut plates that were installed, just a few shown on the screen. But by eliminating the mechanical fastening system, we were able to eliminate 1,500 additional holes. Now, if I were to put 1,500 additional holes into this structure, what's the one thing I know I'm going to have to do to that structure so that it'll perform and not fail? I'm going to have to make it thicker. So by using bonding, I can take high performance materials as they're designed, utilize them in their thinnest configuration, and steal back weight penalties from additional holes. So actually, bonding allows me to fly structure thinner and lighter, reducing weight. Now we could go on and on about reduction of weight. We could say that because I'm flying it lighter, I can fly it further, I can fly it with more payload, I can fly it with more attachments. Number 7, it avoids errors in rework. One of the key problems in manufacturing for aerospace platforms is the drilling of holes. By using a bonded fastener, we can eliminate 2/3 of those holes, ideally 67% of the drilling operations. And if we can eliminate them before you have to drill them, we can eliminate the rework even before you have to follow the process. Lastly, number 8, preserving structural integrity. In this example, you can see a standard nut plate that requires 3 holes. The Clickbond nut plate requires 1 hole. So what does that mean as far as preserving structural integrity? Simply put, I come back to that same example I used for weight savings. If I can eliminate the holes, then I can eliminate fatigue propagation. I can eliminate cracks. A propagated crack between a rivet hole and a structure hole happens all the time. So let's eliminate those holes, let's preserve that structure, and let's fly it light. Now, many people are still skeptical about bonding, even though at Clickbond we've been doing it for over 30 years. When we discuss bonding as an alternative, the question arises, well, what data can support the equivalence of a bonded component versus a mechanically fastened component? Well, to dispel that myth, we dove in and did some testing. On the screen is a photo of the failure of a standard nut plate that's been bonded and a standard nut plate that's been mechanically fastened. Notice the failure mode is exactly the same. So what I'm showing you here is that the yield strength of a metal base is weaker than the bond strength between the metal base and the structure. And just for clarification, that was to a top coat. That was not to metal to metal. Metal to metal is going to be your ideal situation when it comes to bonding. So there are multiple faying surfaces under that nut plate that we were able to overcome. So the picture's great, but let's look at some data. So here's the data plot from that test. Down here is the minimum requirement. Notice that every instance, the performance of the bonded nut plate well exceeded, 2 times exceeded, the requirement of that fastener. And you can see that in all the box plots above. But hold on a second. You say, well, they're all well above, so how can we then look at, I'll say the performance criteria of a bonded nut plate versus a mechanically fastened one? And here's what I'll say, is this is the failure. So let's look at what happens if you had that failure for both examples. If you had the failure for a bonded nut plate, what would happen? The technician would go in, remove the adherence of the nut plate base, re-energize that surface using an abrasion and a solvent wipe, prep a new nut plate, pull it in place, create the installation, the structure's safe. Should it occur with a mechanically fastened version, the first thing the technician has to do is carefully drill out all of those rivets. If he's able to perform that and not damage the structure, he can move to reinstalling another component. But I can tell you that the risk is significant on them damaging the structure doing that drilling operation, which takes me back to one of our key points of bonding is in repair, excuse me. So, who relies on bonding? Well, I'm here to tell you that many commercial and defense programs currently take advantage of bonding where conventional manufacturing just isn't practical. The takeaway is that the aerospace industry has embraced this concept of bonding, and as we look to the future, which of you would bring adhesive bonding which of you would bring adhesive bonding technology into your designs? Our hope that this presentation piques curiosity and asks that question of how you and your teams could work with a company like Clickbond to change your whole approach. This brings me to the concept of eliminating excess holes. It's at the core of who we are at Clickbond, and it's a drawback for mechanical fastening systems. The additional holes create more time and more risk on your airframe. But more so, there's a lot of time that is taken to select high-performance materials So why add holes and lose those benefits, treating them in the same manner that you would treat aluminum? It just proves to be counterproductive. Clickbond's elimination of holes from structure had led to advances in aerospace, marine, and ground vehicles. With bonding, you can go from 3 to 1, from 1 to none, and if you've got them, protect them. Embrace bonding and maximize your design. So this brings me to the end of our presentation for today. But I have one last thought-provoking question for each person here. What are you designing today? But more so, what are you designing today that will affect our world tomorrow? How might bonding give you freedom and the capability to design things never thought of before? How might bonding change your whole approach? Behind me, please scan the QR code if you'd like to learn more about bonding. And if you'd like to know more about Clickbond, please visit clickbond.com. I thank each one of you for your time today. And if you have any questions, I'd be happy to answer them. Thank you.
Thank you, Bill. Does anyone in the audience have a question? Outstanding presentation, Bill. Thank you so much.
Thank you so much.